Hello AP Chemistry and welcome to Chapter 15, Equilibrium. So, in the previous chapter, we talked about the concept of kinetics, right? How quickly a reaction occurs, right? The change in concentration per unit time, right? And it was important, right, that one, we knew the units of what a rate was, right? Change in concentration per change in unit of time, right? And then we knew what a rate law was, and then we knew the ways to find a rate law, right? And we understood the constraints of what we were talking about, right? Like in that this only talks about the rate, the speed with which something can happen, right? And it doesn't talk anything about the extent to which something happens, right? That's a different discussion. We have assumed also through all of this year and a half-ish of chemistry that you've learned, right, that reactions go to completion, right? When we talked sophomore year about the concept of theoretical yield and limiting reactant, right, all of that had the giant assumption, right? And the giant assumption is that, right, the reaction happens to completion, right? That the goal is 100% yield and that 100% yield was attainable, right? 100% conversion to product isn't really accurate and doesn't really describe what's happening very well, right? Thus, equilibrium, right? Which talks about where a reaction actually comes to rest, and every reaction is unique and different. So let's start talking about equilibrium, right? Ways that we can define equilibrium, right? So first of all, here's a process. And if I were being more thorough, I would have done the arrows like this. Not more thorough, it just requires an extra step. And sometimes I just am using the keyboard and not thinking about it. Anyway, so what this says is that N2O4 gas can be converted to 2NO2, right? And this is the diagram from your book, right? That shows that our N2O4, right, is actually colorless, right? Our N2O2 is this brown gas right here, right? And that we go from reactant to product, but not completely product, right? It's not all product necessarily, right? From a macroscopic perspective, right? What happens though, right? As time passes, it looks like it stops, right? And it looks like it stops because one of the ways that we can describe equilibrium, right, is that the concentrations remain constant, right? One of the ways that we can describe equilibrium is that the concentrations remain constant. There's no further change in concentration, which means that from a macro level, when we're looking with our eyes, right, the color isn't going to change anymore, right? The amount of precipitate seems to be constant, or I don't know, those are the two most easy ones that we can see with our eyes, right? But it appears as though nothing else is happening, right? From a macro level, because one of the definitions, right, no further change in concentration, right? If we think about it from a more, what that means from a different perspective, right? If we look at these graphs, right, so here we have time versus concentration, right? So like we said, here we have NO2, right, which was our product. So it was something that was produced, right? Here is our reactant. And over the course of time, the reactant is consumed. So we see that it decreases, right? And our product increases until eventually this part is marked as equilibrium, right? And that part is marked as equilibrium on the graph because that's where the concentrations are constant. If we think back to what we talked about in the previous unit, right? We talked about instantaneous rates. And how do we find an instantaneous rate? Right, slope of the tangent line at time t, right? And if we look at what that means, right, when we hit this part where it's a plateau, the slopes of the tangents are equal, yes? When we hit that plateau, the slopes of the tangent lines for both NO2 and N2O4 are the same, right? Therefore, their rates are the same, which means that we have reached equilibrium, yes? Right? Then from a different perspective, right, we can look at it on a rate versus time graph, right? And again, our rates are equal when we reach that point. Yes, does that make sense? And we should be able to look at a graph of either perspective and put those two together, right? So again, macro level, the concentrations no longer change. From a micro level, the reason those don't change is because the rate forward is equal to the rate reverse, right? Now, embedded in that concept, right, in order for the rate forward to equal the rate reverse, right, the little thing that is built in there, right, is that it must be a closed system, yes? And we referenced this back when we talk about vapor pressure and gases, right? Because we said that every single liquid has a vapor pressure, right? A certain amount of it that evaporates at that temperature and creates and stays in gaseous form, right, over the liquid as long as the vessel is sealed, right? In that gas cannot escape. If that gas can escape, vapor pressure is never reached, right? And this is that concept, right? Where this same thing is true, right? In order for equilibrium to be reached, we must have both N2O4 and NO2 present in order for this process to go both forward and backwards, right? Because that's what we're saying, right? We're saying that the rate forward is equal to the rate backwards, which means that we must have reactant present and we must have product present in order for this to work. Yes? All right. Thank you for listening. Be good. Stay tuned for the next one where we start talking about K and what it means. All right. Thanks for listening. Be good, and I'll see you soon.